Alright, I guess I'm making a video, I think. So, yes, this is draftphysics.com, debatephysics.com, also video presentation and such. So, I did find another person doing some experiments, another teacher, I guess. Don't know much about him. Found a web page that had some, interesting experiments with propellered cars and pretty decisive in terms of the outcome. So I thought that would be good fodder. And then I found his YouTube channel, and he has some videos that are, well, actually, the video is pretty bad as science goes. It's just really kind of a joke. But we'll play it anyway, if I can find it. Should be able to do. That isn't it. It's one of these. There it is. Okay, so I'll get rid of that and draw for a bit, and that should work. All right, and I will draw with the pen that's missing. Interesting. Yeah, whose fault is that? I don't know. I'll blame somebody later. Probably be me, because I'm the only one who's usually around. All right, so what you're seeing above is just this idea of an air track. I think no, it's those are cars with wheels, and they have a fan on them, and so they're both getting the same force blown on them, so to speak, the same motor force for the same period of time, and one weighs half as much as the other one, and it obviously goes twice as fast, the one that weighs half as much. And so it's sort of a verification of this argument about levers, that the real conservation is that if you do put the two mass, okay, going 1v in, you are going to get a one mass, okay, going, 2v out. You're going to conserve the momentum. You're not going to conserve the kinetic energy. Okay, that's going to be the reality. So he also does the same experiment with a 4 mass. So a mass 4 times as heavy, and it goes much, much slower, demonstrating 1/4 of the velocity. So it's just a pretty good piece of evidence, okay, that, people really can't be arguing that the same force can't create twice the velocity in the half mass object, that there's not some sort of inertia. So there's no inertia on that yellow car that's stopping it from going twice the speed. There's no 1.4. Same force, it's going twice as fast when the same fan is blowing the same amount and pushing just the same hardness for the same amount of time and all that crap. It's just a pretty clear piece of evidence that the momentum is conserved and kinetic energy is made a mess of, because now you have the same exact force creating in one circumstance something with twice as much energy. The half mass, the one mass going 2v, has twice the kinetic energy of the 2 mass going 1v. So kinetic energy is way out of whack, but they have exactly the same propeller. The same exact force has been pushing on both of them. It's been converting the force into motion, the same for both of them. And yet one of them has somehow magically created twice the kinetic energy out of that force, and the other one is somehow wasted half the energy. Half the energy just wasted somewhere. Wasted where? There's no evidence of the waste. There's no place to go find the waste. So again, it's pretty decisive evidence. Right. So then the second thing, when I found this other video that he did, he was talking about the Mythbusters, video, which 3 or 4 years ago we went over pretty thoroughly in videos, and it was a couple of experiments done, and the real point of the video wasn't the point of the video, in the sense that what they revealed in doing the video was, again, that kinetic energy doesn't work, because they crashed cars, in a couple of different ways to prove a point. And the kinetic energy thing just didn't show up, and that was just a fact. So what you start with a car, okay? You say this is the car's normal size, and if you have a 50-mile-an-hour crash, you end up with that much crushing, and if it's a 100-mile-an-hour crash, it's twice as much crushing. So again, showing perfect conservation of momentum as a concept. Perfectly conserved makes perfectly good sense. There's supposed to be 4 times the crushing at twice the speed by the kinetic energy theory, and there wasn't. And so this also relates to the other experiment they did, which was, crushing clay. Okay, and the idea was to have 50-mile-an-hour clay hit 50-mile-an-hour clay, and the simple truth is that that's the same thing as 50-mile-an-hour clay just hitting a brick wall. Because the only thing you can really do is in the experiment, you're going to go from 50 miles an hour to 0. Nothing else is going to happen. This is going to go from 50 to 0. This is going to go from 50 to 0. That's all that happens when they hit a brick wall, is they go from 50 to 0. Same difference. Same exact thing for them. Their experience will be exactly the same. The experience of the driver. But if there was somebody in here, okay, if there was somebody in between, and they were doing the crushing, if they were the thing being crushed, right? So the clay got half crushed over here and half crushed over here, and that makes perfectly good sense because you have 2 units of clay. But if you replace it with 1 unit of clay, you would expect that unit of clay to be crushed twice as much. And it was. So that's sort of another point proven by the experiment. So not only does it prove that there's no evidence of kinetic energy in the crushing of cars, it perfectly makes sense again that the way energy is distributed is just momentum, and you can always trace the momentum. So the kinetic energy theory really doesn't play any role at all in any of these mechanics. You can certainly, if you don't concede to the existence of this fake scalar, non-directional, magical energy, you're not going to run into any problems. You're not going to really predict these experiments wrong. You're going to predict them right. And you're not going to be making a mistake like he's going to make in this example. All right, so, with that context, we'll play the video, but it's just, I don't want to be picking on people, but this is even in its own comments, there's a bunch of people telling him this is a garbage. You're not being a very good example of a teacher, frankly, because it is that. I mean, this is worse than the amateur experiments. I mean, a lot worse. It's really bad. But anyway, we'll play it. I mean, it's almost like he's doing it's like he's not taking the physics seriously at all. These are real subjects, and they need to be taken seriously. But I don't want to. It's nothing of no offense. It's your choice to be a little bit casual, but I'm just arguing that casual doesn't do science any good.
Let's talk about collisions. So a long time ago, there was a Mythbusters episode. I honestly don't even remember which one it was. But they wanted to do a head-on collision. So they had 2 cars, and they wanted to do a 50-mile-per-hour versus a 50-mile-per-hour crash like that. And it's not easy to do if you don't have people in there, because you got to get them both move. They got to both be lined up and everything. An easier collision would be to hold this one stationary and then just drive one into there. And then, of course, that's not the same thing. And they said, oh, my track's not level. And they said, well, what if instead of a 50-50, I do a 100-mile-per-hour, 0-mile-per-hour collision? Is that the same thing? So let's explore that question in a little bit more detail.
So he doesn't really explore it in terms of diagramming it. And if you diagram it, you find out that, there's nothing to say, really, okay? All you can say is this one car, in the 50-50, 2 cars hitting each other, there's just nothing else they're doing. It's not like the cars do bounce or do anything else. They crush. So as long as you're crushing cars, it can't make any difference. Now, if you make them if you make it so none of the energy can be absorbed and it's a perfectly elastic, well, then it's going to mean both of them now are going to rebound, which means they're going to have a huge difference in their G forces because they're going to reverse their direction, and they're both going to experience what would be twice as much G force change than they would have had if they didn't crush. I mean, if they did crush. So I'm just saying if they crush something, then it just is 50 to 0. But if they're uncrushable and they're going to bounce, well, that means they're going to go from 50 this way to 50 that way, which is obviously twice the G-force transition. So it's going to make a mess out of them. It's going to make twice the mess out of them. But obviously it's just you're just arguing that, yes, in one case you're absorbing the energy and using it and turning it into heat. In the other case you're not using it, and so it's still in linear motion. So you have to see it in linear motion somewhere. And he doesn't really even get to that part.
We want to look at the damage done to each car. So I have a little aluminum foil bumper that can collapse when there's an impact. So let's do
this is
a fit, and they would
obviously a ridiculous sensing device. I mean, it's just so bad, you know. So obviously you can't do any clinical testing.
Both have bumpers, but I'll only put bumpers on one of them because, you know. So let's do a slow collision. I'm going to push these very slowly towards each other. I have some launchers, but I'm not going to use them.
Right, I'm not going to bother doing it in any kind of scientific way. And again, the launchers are dubious, okay? Rubber bands stretched, you know, violating, you know, Pythagorean theory in terms of, you know, the stretch isn't going to be commensurate to the amount of stretch in the rubber band, so you got to be very careful about whether you're stretching it twice as much or not twice as much, and lots of things.
Going to kind of estimate. I'm going to push them very slowly, and let's look at what happens during the collision.
All right, so
here they go.
It's so ridiculous. I mean, obviously these two cars weren't moving the same speed. Obviously, this is just a waste of time.
So you see it compressed the bumper a little bit. Now,
no, you didn't see any. No, it's just useless. So it's like a 50% elastic collision. I mean, it just demonstrates nothing because, you know, it's right in between. It's not fully elastic and it's not fully inelastic. So it's useless.
I didn't get a completely. I would like for them to stop afterwards, but they don't stop. That's fine. Just imagine they stop. Oh, that was bad. They weren't going the same speed. Really slow. Here we go.
Yeah, obviously the car had already stopped. So again, useless experiment, not even close to meaningful, and obviously not demonstrating what it claims it demonstrates.
Well, you get the idea. I think you get the idea.
I get the idea that, man, I'm lazy, but you're really lazy. That's the idea I get. Wow. You couldn't just be bothered at all, right? You have the cars, you have the track. Let's not even bother doing anything scientific with it. Okay, I get that. No, I don't really get that.
So, if I have an internal force, if red car pushes on blue car the same that blue pushes on red for the same amount of time, then they have to have the same change in momentum. Another way we can say that is that the momentum of the collision before is the same as momentum.
So it's just ridiculous to talk about things that are moving having zero momentum, right? So I mean, it's just so stupid to do this. Somehow motion has a direction, so momentum somehow cancels and doesn't exist, when obviously what the experiment will demonstrate is its existence. I mean, a nuclear bomb has stuff going this way and stuff going that way. Nobody, you know, and if you did one in space, it would be perfectly symmetrical in all directions. So why the hell would you sit there and argue it doesn't have any momentum? I mean, it's just ridiculous. It's one of these scientific things, you know, they say, and it just doesn't make any sense. Like me saying this pen, it doesn't matter how fast I lift it, I do exactly the same work. So if I take a whole day to lift it, that's the same amount of work as if I lifted it like that real quick. Now, it's not the same amount of work. You know, it's not the same amount of force hitting the pen that has to go through me. It's a whole bunch more force the longer I take to The longer I'm supporting this pen, the more work I'm doing. The more work the system of me and the ground is doing, holding the pen up.
Afterwards. And so momentum, we use P. I'll use the scalar version, is mass times velocity. So in this case, let's say I have mv going that way, negative mv going this way. Wait,
All right, so negative mv, it's just like, what the hell are you talking about? I mean, there's no such thing as negative motion in the universe. It just isn't. There's not positive motion. There's not negative motion. There's motion. Motion is energy. Always.
which is your negative direction. Negative would be, that's positive. This one's negative. Negative mv, positive mv. So the momentum before the collision is 0, and then if they collide and stop, the momentum afterwards is 0 too. So
if they collide and stop, which means if they have collidable, crunchable bumpers and absorb the energy, but if they don't absorb all the energy, if they don't find some way to convert all the energy into heat or convert it, period, into some other kind of motion besides linear motion, then, some portion of it's still going to be moving in a direction, and it's not going to be negative and positive. It's not going to have any orientation. It's just going to be motion in a direction. It's going to be mv, not positive mv, not negative mv.
that's all fine and dandy. What about energy? The amount of damage done to the card comes from the energy, because if this has a 1/2 kinetic energy.
So this is where he'll just go completely sideways and just make up a story, and that's all he is. He's just going to make up some fake story. So it's not an experiment. He's not doing anything clinical, so he can just get away with just claiming something that doesn't make any sense, that has both momentum and kinetic energy. Well, they can't have both because the two numbers don't agree with each other.
I should write that down. K is 1/2 mv squared. So since v is squared, and because it's the magnitude of the vector, it's always positive. So this one.
So it's the magnitude of the vector, but it's not a vector, right? So this is they can't even keep their jargon consistent. He just said the magnitude of the vector. There's no vector, right? It's scalar, so there's no vector.
Doesn't have negative kinetic energy, and this one has positive. They both have positive kinetic energy.
Right. Well, it's just, again, they both have positive momentum, frankly. And that's the absolute truth. And it's the momentum you can find. You can see where it goes. You can measure the amount you convert to heat, and you can see the amount that stays as motion, as mass is moving.
So this has 1/2 mv squared, this has 1/2 mv squared, but after they collide and stop, they have 0 kinetic energy. So where did it all go? It went into the bumper.
Whatever. So again, says you that there was this extra amount of energy now because you decide to square the velocity for no good reason and just make a claim that there's more energy.
Now let's switch to the case where I hold this one stationary and I push this one twice as fast. So I'm going to push this twice as fast, approximately. Let me fix my bumper back the way it was.
So this is the big fake claim. So what the Mythbusters demonstrated was this doesn't happen, in the sense that there's no evidence that your extra kinetic energy will be revealed in any extra bumper crushing. It doesn't happen.
And you'll notice that it compressed a lot more.
Oh, yeah, it says you. Yeah, right. Sure did. Okay. So too ridiculous, right? Just way too ridiculous.
Okay. So in this case, I double the speed of this one, so it has twice the momentum.
Right. So he's saying because it's one car moving twice the speed is somehow twice the energy of two cars moving half the speed. And it isn't. It's not twice the momentum, and it won't do twice the work, and there's no evidence it'll do twice as the work. It won't create twice the heat. There's no evidence it creates twice the heat. And your own experiment right there shows that twice the force is going to be okay, twice the energy, in the sense that I can either put 2 fans on one of these carts and have the same cart, or I can just have the mass and I'll get twice the velocity, which is exactly what the law of the lever claims, and exactly what pulleys do, and exactly what everything does, and it's perfectly consistent and perfectly rational. Momentum works as a theory. It never fails, and there's absolutely nothing the kinetic energy theory can do except make a mess. And so that's all you're doing is making a mess out of physics and such. So I guess I ought to see if there's anybody. Nobody's chatting. All right, 3 viewers. Okay, so I don't know what the volume. Can you hear me okay? Somebody could just say something like, yes, sound is okay. You can hear his video okay. It's always good to know that kind of stuff. Yeah, it's good to know, but you have to have somebody that'll tell you. So anyway, let's continue.
This one has 0 momentum, but still after the collision, the momentum's 0, so it seems like it's the same thing.
So again, it's saying after collision, the momentum's 0, right? And you just made a whole bunch of heat then, you know. So if there's no linear motion, then there's a bunch of heat somewhere. And heat is momentum. It's movement of little objects. So all you did was take motion in big objects and you turned it into motion in little objects. That's the conservation. That's the physics Descartes understood 400 years ago. And it's really bizarre that you would deny that simple logic and choose to believe in this scalar, magical, wooey, living force, childish, sparkly, scalar energy. You know, it's just, it's silly.
But if I double the velocity, I'm going to get 4 times as much kinetic energy.
Right, except you'll never demonstrate it. You'll never do 4 times the work. So you'll never show us it doing 4 times the work. You'll never show us 3 times the velocity doing 9 times the work. You're never going to show us 4 times the velocity doing 16 times the work. And you'll certainly never show us 25 times, okay? 5 times the velocity doing 25 times the work. That you will never show us.
So now only 1 car is moving, but still there's a 4 times 1/2. So I actually get double the kinetic energy. If this one's going 100 and this one's stationary, or they're both going 50, this would have double the kinetic energy of the system.
Which makes absolutely no sense, because again, your own experiment sort of demonstrates you can create that scenario. You can make something go twice as fast by just having its mass, so it's not a problem. Same force is creating twice the velocity in the other object, and there's no evidence it's going to do 4 times the work. There's no evidence it's going to do twice the work. There's no evidence those 2 objects don't have exactly the same momentum because they have exactly the same force being put into them. They've collected exactly the same force. How can one of them have more energy when they've collected the same exact amount of force?
Some of them both going together. So that means it's going to give more damage to the car.
All right, so that's just a big...
Now, there is a way to...
It's a big says you, okay. So you reference a Mythbusters video that I guess you didn't really watch, and you completely saying it showed things that it didn't show, because it showed exactly the opposite. And they had to contrive an excuse for the absence of any evidence of kinetic energy, and then they started talking about how, well, you can't crush a can because it crushes unevenly, and other bullshit excuses to say somehow, to rationalize the fact that their experiment shows no evidence. I mean, it wasn't even like 2.2 or 2.5 or 3 or 3.1. It wasn't anything indicating anywhere, like even indicating you're going to get to 4 someday. Okay. You never got over 2.
Fix this. So that's what the Mythbusters did. They said, hey, what if we collide it with a wall going 100 and it did a lot more damage?
Wrong. So it didn't do a lot more damage. So it's exactly not what the video showed. It was exactly the opposite. It showed It's only twice the damage. That's it. 50 miles an hour, 100 miles an hour, twice the damage. That was it. That was the big reveal in the video, essentially. That was just a bit of a surprise to everybody because, yeah, theoretically, there's supposed to be 4 times the damage, and there was only twice.
And that's just the way it works. On top of that, if you collide it with a wall.
So again, it says that's the way it works. So it's again just the same sloppy physics where they just say, well, they did this Eddington experiment, and then they did this slit experiment, you know, and they put electrons in it, and then they put golf balls in it, and then they put dogs and cats in it, and yeah, it always comes out exactly the right way. It always comes out our way no matter what we put through the slits, hamburgers, hot dogs, doesn't matter, it always works. I mean, it's just such bullshit.
All that kinetic energy goes into one car, whereas if you collide 2 cars together, then both cars get damage from the kinetic energy.
So there's no evidence of any of this stuff about what gets damaged. Obviously, in real cars, they crushed about the same amount, the same car, they crushed equally. That's what was demonstrated. And then they did it with clay, and the clay crushes consistently. You know, half the crushing in one blob of clay over there, half the crushing in the other blob of clay on the other side. Obviously, if I use 2 springs in an experiment, the 2 springs are going to be absorbing the energy independently, and if I used 1 spring, then the 1 spring would be crushed twice as much, blah, 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 blah.
But there's a way to fix it. Watch this. Okay. This is just an approximation. I wish my thing was level. I'm going the wrong way. Raise that. That's why. Raise it. Okay, is that level? No.
This crap you can buy, you know, is always, you know, it's pretty rickety. You know, for $500, they do give you a pretty cheap scientific project experiment thing.
Okay, that's good enough. So here we go. I'm going to push this one twice the speed. I'm not going to hold the red car. Okay, here we go. So it did.
Yeah. So what you did was again is a not either. It wasn't elastic and it wasn't inelastic. It was somewhere in between. So part of the motion was conserved as linear motion, and part of the motion was converted into heat of your crushing of the foil. But that's all you showed. You didn't show anything else. There's nothing magical in here. You didn't show how it's twice the energy or any of that crap. So bullshit.
It didn't compress the bumper as much as it did when I held it. Let's just repeat the holding time type.
Yeah, duh. So if you hit something that can move, you'll use part of the energy moving the object instead of crushing your bumper. So if you hit a car that's light, you're not going to get as much damage and you're not going to feel as bad. And if you hit something heavy that you can't move, then you're going to feel a lot worse and you're going to get a lot more damage. Duh.
See, that compressed it a lot more. So what happened here is if this car is not moving, then I have, yes, I have more kinetic energy in this if I double the speed.
Right, so you don't have any, there's no more energy. You're just changing what percentage of the energy you're converting into heat through bumper crushing.
But after the collision, this one recoils in order to conserve momentum. They're both moving that way. And so that means it has some kinetic energy. This gets some of the...
Yeah, it's silly to talk about conserving momentum and then getting kinetic energy, because obviously, again, if you're going to... Anytime you're going to convert energy from masses, different masses, or different percentages of the energy, you will always not conserve both. You can only conserve one or the other. They both can't be conserved. Just an absolute fact.
Kinetic energy. This has some of the kinetic energy, and then some goes to the damage. And it turns out that analyzing it either way is the same, because in physics we have reference frames.
So it's obviously not analyzing it. Is not the same. If you allow if you don't allow anything to crush, the impact for both cars is going to be 100-mile-an-hour impact. In a sense, their change in G-force effect there is going to be twice as severe as if they were hitting a brick wall going 50 miles an hour. So, I mean, but that's true of the brick wall. If the brick wall doesn't, if that's also nothing crushes, it's the same thing. That experience is going to be just as bad. So, I mean, you can't change. All you're changing is if you don't allow anything to absorb the energy, the total energy in the event for the G forces anyway. Not the. There's no crushing forces, so we're just talking G forces. Is the complete reversal. That is, you go to zero and then accelerate in the opposite direction. So obviously the G-force impact will be twice as impactful on a person driving a car, whether it's elastic or inelastic, will matter dramatically. But it's not more energy. Reversing the direction is not more energy. I mean, you could just make that argument that you can bounce a ball bearing on an anvil, and frankly, you're not making more and more energy every time it bounces. You're not doing that. You're conserving the energy you put in because it's just reflecting. You're not creating any energy. You're just not using it. You're just reversing direction. Reversing direction is essentially for free. You can do it with levers, you can do it with pulleys, you can do it with lots of mechanisms where you can pull down and something will move up. And it's perfectly reasonable.
Where we measure stuff, and there's no absolute reference frame. I'm using
so we know the reference frames are irrelevant, so
this room as a reference frame, but the room's moving. So if you were outside of the Earth looking at this, you would see these cars already moving because the Earth's moving. Now, the Earth's actually rotating. Okay, so that's a little bit different. Let's just pretend.
Yeah, don't even bring up the subject of what's moving, because now that movement can be shown in these experiments because everything in the room is moving the same speed, and they're all doing that together, and those speeds aren't going to be changed in any way that doesn't change them mutually. No, you can't change. You're not going to undo their already consistent starting condition. So it doesn't matter what their starting condition is.
But if I change to a reference frame, imagine I have this one stationary, and I change the reference frame of the center of mass, so it's moving half the speed in that reference frame, then we get back to the same collision where this one's going 50 and that one's going 50 that way, and it's the same thing. So we shouldn't disagree on the amount of damage, because that's the real...
All right, so again, the real argument is whether you're going to convert the energy or not. So if you're just going to exchange it, and you're not going to convert it into heat, then it's the impact on something made out of flesh that could be affected by G forces will be dramatically different.
Real thing that we see based on our reference frame. So you can replace a stationary car, a 50-50 collision with a stationary car and a moving car twice the speed, but you got to let it recoil, and then it works.
Okay, but it doesn't, no, that's true. So it's always going to be the same energy. It's either in linear motion or it's in heat. That's it. So it's only going to be in two places. It's either dissipated as heat or it's still as linear motion. And you can have any percentage of that as you want. You can have fully elastic or you can have fully inelastic and everything in between. And in every case, you'll conserve momentum. But what you won't always conserve is kinetic energy if one of those carts is twice as heavy as the other, which the experiment sort of shows. I could change this to the other image. So let me see if that'll work. Of twice, the 4-to-1 animation. Yeah, there it is. So that's 4 mass to a 1 mass. So the same idea, same force is pushing. Obviously, 4 times the velocity is acquired. The chart, he has it all charted. So in that experiment, he actually uses real software, you know, the distance measuring device, all that kind of crap. And the chart indicates exactly what it looks like. Okay, the yellow car is going 4 times the speed that the blue car is going, and it's exactly 4 times the mass difference. So again, perfectly proving twice the force, twice the motion, 3 times the force, 3 times the motion, 4 times the force, 4 times the motion, in the sense of the proportion to your mass. So if I reduce your mass and apply the same force, obviously I have every reason to expect you to go twice as fast. I don't expect you to go 1.4 as fast, okay, as physics claims falsely. Thank you for the volume report and such. So, all right, so I guess we could go look and see if we can find another video by this guy. And there is another one here, so I guess I could try this one first, and then we can back up. So this is dot physics. And this one says, is a 50-50 head-on crash the same as a 100-mile-an-hour crash? And again, the trick is, for gooey human objects, it matters. You know, it's not going to matter to a piece of, like to this crayon. It's not going to matter whether I jerk it this way and then jerk it that way. It's not going to be affected. But obviously a human being, okay, that's going to have a skeleton full of water, you know, jiggling it's going to make a mess out of the water bits. They're not going to oblige, and they're going to go this way and then smash this way, and then they're going to be smashed into the other side. So they're going to be made a mess of. Right. All right, so let's do that, I guess. I mean, it's just interesting that somebody else had the same thing from that Mythbusters.
I'm done spending an obscene amount of money on takeout every week. Done.
I'm getting back on track with Factor. Fresh, never frozen meals.
I don't know how to make food.
Welcome,
people.
and I would like to give a quick introduction in case you're just coming here. This is Physics Explained, and I do physics. And I don't do, I'll just give you the answer. No, I'm trying to show you exactly.
Oh dear, you're not going to give me the answer. Oh, yeah, well then, fuck you. Yeah. Oh God, I hate these. Let's not do the answer thing. That's like a Professor Lewin. Well, it's a thing that happens, and think about it. You know, because he doesn't have a good answer. So they just sit there and pretend there is a good answer when there isn't a good answer. All right, anyway, we'll listen to this, though. I'm sorry, I already interrupted. 15 minutes to explain something pretty simple.
Exactly how these things work. So if you're interested in questions like this, or you're trying to get help with your physics, then just go down and subscribe wherever that is. I do low-key stuff, but I kind of know what I'm doing. So this is a great question, and I have my props here.
It almost sounds like the same guy, right? Yeah. Oh, dear. Well, let's see.
There we go. Here's my other car. Okay, so this is a question from Mythbusters, an earlier season of Mythbusters, and I should note, yes, I was the science advisor for Mythbusters, but I did not work.
It is the same guy. So, you know, this is pretty, you know, the internet's getting so bad. There's so many people have 15 channels. And then you got all these people doing fake Feynman videos and fake everybody videos. And, oh, man, it's just, I didn't think, you know, the information superhighway is just going to turn into the fakeidation, you know, claymation superhighway. I mean, it's nothing, that's going to be real. It's all CGI. It's all fake.
Work on this episode. A huge Mythbusters fan.
So, yeah, and it's just so obvious that they, somewhere in the middle of the episode, they said, hey, you know what? These results are totally fucked up because of kinetic energy. You know, we were supposed to get 4 times the crushing, you know? And then they had to, you know, think about it and figure out a way to get out of their own episode without, you know, making the claim because they didn't have the balls to say, hey, we just proved kinetic energy is bullshit. That's what they should have said is, You know what? We just proved that this stupid Leibnizian nonsense, this stupid squared velocity crap, doesn't have anything to do with reality. That's what they should have said. But they were too cowardly.
And I don't know what else to say about that. We can talk about Mythbusters if you want, or MacGyver, also the science advisor from MacGyver.
Yeah, same guy.
But
So anyway, you just saw the care and clinical precision of his experimental procedure, and you're just saying, oh fuck. But like I said, this is, up here is pretty good, so that was okay. All right, did that one pretty well, but yeah, that last experiment was just so bad.
let's talk about this problem. So here's the situation. They wanted to see what happened.
So he has a different channel, Dot Physics. So and this one has 55,000 subscribers. It's just so deceptive, frankly. I don't like this. I don't like this kind of crap on the internet. All these people who have all 15 channels and shit, and it's just bullshit.
If you crash two cars together, so they take car A and B. In the first case, said okay, they're both going 50 meters per second. The answer is actually 50 miles per hour, but that's fine. And they go nah, and they crash, and you can make your own noises there. And
yes, without a spring, okay, non-elastic.
And then they said, hey, but what if? Why don't we just take car B? And this is kind of hard to make two cars collide with no one in there, to make them both hit. It'd be much easier if I could just put this one here and then double the speed of car A, so it's going 100 miles per hour and crashes into that one. And is that the same thing? So it's 50-50 crashing together, the same as holding this one and then crashing in this, going double the speed. Because still, the closing speed's 50.
Right, so if it's inelastic and you're going to convert the energy into heat, it won't make any difference. If it's elastic and you're going to conserve the motion as linear motion, you will cause a G-force event that will be twice as dramatic for a passenger in one of the cars.
And 50, so it's 100, and this is 0 and 100, so it's still 100. So, spoiler alert, it's not the same thing. Okay, so let's show you
It's the same thing for the cars.
why it's not the same thing. I will show you why it's not the same thing, and I will show you when it would be the same thing. Okay, so that's what I do, and I just realized this car doesn't have wheels. There. Okay, so let's start with this case. It's both cases we're going to consider a completely inelastic collision. So in a collision, there's two things that we need to deal with.
So we know completely inelastic just means all of the energy will be converted into heat. The deformation is almost irrelevant in a sense, but it's always usually going to be proportional to the energy in, how you do that conversion, how you make the heat. But the fact is that would be the ideal thing to measure is the temperature. What you actually, how much increase in temperature you created through the collisions.
I can say the total momentum before in the x direction is the total momentum afterwards too in the x direction. So where momentum is in the x direction is mass times velocity in the x direction. So we're dealing with a one-dimensional problem here, so I'm not going to use vectors. This comes...
Not going to use vectors, except you're going to pretend there's zero momentum going in because there's two opposite vectors. Whatever.
From the idea that if there are... the momentum principle says F net x is the change in momentum in the x direction over the change in time. And so since car A pushes on car B with the same force that car B pushes on car A, they have equal and opposite forces, so they will have equal and opposite changes in momentum because the time's the same. So that's where
So all of that mush doesn't really mean anything. We just know that you're going to conserve the MV in the sense that it's all going to be converted into crushing.
This comes from. Now, what about the collision? So one of the things that we need to consider for the collision is the kinetic energy. which is 1/2 mv squared. So if these two cars collide and then stop, they lose kinetic energy and it has to go somewhere. Where does that kinetic energy?
So again, this is the baby talk part, and it's unfortunate that you have two cars that weigh the same and you're just plowing them into each other. So obviously the kinetic energy numbers are just made up. You just make up fake energy in, fake energy out. But it's all fake.
Energy go? It goes into this.
So
This
obviously
is
in the
physics
other,
explained, and
in the
I
other example,
do
that's exactly the same place it
V1
went.
also in the opposite direction.
So why the hell would
Formation of these two cars, see, that's their crashing.
yeah.
1/2 m.
So why wouldn't you draw the same exact thing for the momentum? That's exactly where the momentum went, is into the crushing. So again, this is just ridiculous nonsense.
V squared. So if these two cars collide and then stop, they lose kinetic energy and it has to go somewhere. Where does that kinetic energy go? It goes into.
It goes exactly where the momentum went, into the deformation of the funders, and the deformation is the heat generation. So now it's heat moving through the universe.
This.
You forgot the wheel.
It goes into the deformation of these two cars. See, that's their crashing. You get it? Okay. So we can call this some change in internal energy. So if I say there is.
So whatever. Again, what's this internal energy thing? What are you talking about, internal energy? None of these things have internal energy. It's just bullshit. They have linear motion. That's it. That's the only energy they have, is their linear motion. Yeah, you could burn them in a fire. You could nuke them. But we're not talking about, turning all their atoms into electrons and loose electrons and protons. We're talking about what's their energy in terms of the pragmatic, practical capacity to do work without melting them or consuming them in some nuclear process, doing alchemy on them. Short of that, I mean, it's just such bullshit.
Is no work done, then the change in kinetic total plus a change in internal energy would be 0. So
again, it's just kind of silly to say no work done except for the crushing and the heat. There's no work done. Yeah, except for the crushing and the heat.
that means that this change in kinetic energy is something that I really want to look at. What's the change in kinetic energy here? What's the change in kinetic energy there? If the change in kinetic energy is the same, then we're all good.
So whatever that much was. So let's see this little question here. First, I would wonder why the people that produce the Mythbusters not challenge kinetic energy. They could have gotten attention to the subject. Yes, I mean, it's just kind of sad that they are so convinced that it must be true because everybody believes it, that they were too intimidated. I mean, neither one of them are like real physicists, right? I mean, so, these guys don't really have the capacity to start making declarations about how physics works. They're just engineer types. And if they had a physics degree, it was 20 years ago or something, and they're way out of that ballpark now. So that's what it seemed like to me, is that they obviously really didn't have the capacity to make a statement about physics. And they really should have. They really should have, because it was so obvious. It was such a piece of strong evidence, and they should have made it clear that this is just bullshit to talk about some magical coincidence that the cars only crushed exactly that twice as much, and that's exactly confirms momentum and exactly destroys the idea of kinetic energy, and it wasn't 2.2 or 2.5 or 2.7. It just happened that the steel got harder to crush, exactly the right amount of hardness to crush. Bullshit.
Okay. Let's do case A. Case 1. So this is two cars, both going 50 meters per second, same mass, head-on collision. Let's first look at momentum.
I don't know what he's looking at now, but whatever.
So let's put the situation Here's before. I have A. I'll
So I guess this is the 100-mile-an-hour crash.
say this is V1 going that way, and this is B. Has the same velocity but in the opposite direction, so I'm going to call it V1 also in the opposite direction. So for the momentum before the collision, here's after the collision. So I have M V1.
All you have is pounds of pressure in springs if you measured it in springs. So again, if you were crushing clay and you use 2 blobs of clay, well, then the clay gets crushed half as much. If you use 1 blob of clay, then it gets crushed twice as much. I mean, it's that obvious. Same thing. If you're absorbing the energy, if you're inelastically converting the linear motion into heat, it will be exactly the same event.
Plus
For the participants moving.
M negative V1. So this is the mass, the momentum of car A before the collision. This is momentum of car B before the collision. They have the same mass. They have equal and opposite velocities. And this would be equal to 2m times v2. So v2 is the velocity of this thing afterwards. And this is the mass of the thing afterwards. It's one object now of mass 2m. And you see here that this side, if I have m plus m and v1 and negative v1, this has to be 0. So this is going to be 2m v2. So v2.
So again, they're just making this silly argument that you have, you know, 2 sumo wrestlers heading for each other, and that's a 0 momentum. No, it isn't. It's just silly to say it is. It's silly to say it is.
2 equals 0 meters per second, which I already knew that, okay, but I'm just trying to show you how that works. So that's where we have that. Now, what I want to do is to find the change in kinetic energy. So delta K is going to be the final kinetic energy, 0, minus the initial kinetic energy. So it's going to be minus the kinetic energy of this, 1/2 mv1 squared, minus 1/2 m negative v1 squared. Because that one had a velocity of negative v1, but I squared. So
Right, and in the experiment, they're both crushing fenders, so their velocities will be 0, so it just couldn't make any sense to worry about this. It's 0 minus 0 minus 0. How interesting. No, silly.
this gives a change in kinetic energy of 1/2 mv1 squared minus 1/2 mv1 squared, or minus mv1 squared, delta K. Got it? Okay. Let's see if I can fit case 2 on here. So case 2 is similar, but now I have this. A. This has a velocity of 2v1, where I'm still using the same v1 up here, and B is at rest. And then after the collision, they're still stopped, right? Because there's a wall there. So again, the momentum doesn't really make too much sense. I'll write down the momentum.
So you might as well say that the wall has an infinite mass, if you want to be fair. You know, and then pretend you have a gigantic interaction between momentums, but you gave it a gigantic mass. Unfortunately, no velocity, though.
Equation, and I get, because it does show that there is a problem with momentum. So if I write down the momentum before, I get m times 2v1 plus m times 0. So this is the momentum of that one. This is the momentum of that one beforehand. And this is going to be equal to 2m times 0. So that's not conserved.
So we know that it is, in the sense that we know what it's going to do is work. So again, he's going to claim it's going to do more work, but it can't. It won't. It'll only compress 1 spring twice as much and 2 springs half as much. It'll be exactly the same amount of work done on springs. So there's not going to be any evidence of this outcome. It doesn't happen. They just claim there's twice the energy. There isn't, but they claim it.
And that's okay. Okay? And I'll tell you right now, it's not conserved because during the collision, there's an external force on car B, which...
So this is the ridiculous part, right? An external force, like the same external force of us being pushed into the ground. You know, it doesn't make any sense. There's no external energy source. There's just the energy you're putting into the experiment, and that's all there is here. So again, it's just bullshit.
Which means if I take the system of car A and car B, there's an external force.
There's no external energy produced in the experiment, so it's just not true, and there's no evidence of it being true. Again, you're not gonna compress more spring. So if I have two 50-mile-an-hour cars hit a spring in the middle, it's gonna crush just the same amount as if I have one car going 100 and crush the same spring. It's going to do exactly the same thing. No difference. So it's just bullshit to say there's any evidence that there's 4 times the energy. There isn't.
And momentum is only conserved when we have a system with
No, it's always conserved, ever, always, always, always. It's never not conserved, and there are no free sources of momentum. Reflections are part of reality, okay, and they don't require extra energy.
no external forces.
You can change direction for free. Pulleys prove it. Levers prove it.
So this one, momentum is not conserved. What about the change in kinetic energy? Well, let's do that. Delta K. It's going to be the final
I mean, it really is that simple, right? I mean, all of this talk of direction, isn't it all blown up by just something as simple as a lever? I mean, it just proves the point. I mean, I could put a 2 mass in on one side, and I can move a 2 mass on the other side, and I'll conserve most of its energy. I'll lose a little bit to the lever, but most of it I conserve, and all I did was change the direction of a 2 mass. Yeah, that's it.
kinetic energy, that's a K, which is 0, minus initial kinetic.
If I move the Earth, or the Earth has to supply something, then that would use up my energy. That would be non-conservative. I have to use the energy then. The fact that reflection is an indication when something doesn't accept the energy. I push on something and it doesn't accept the energy. That's a reflection.
Energy of this one, which is going to be 1/2 m 2v1 squared minus initial kinetic energy of this one, 1/2 m 0 squared. So you see here I have a 2v1, and up here I had two masses. Okay, but it's not the same because look, this is going to be negative 1/2 m times 4v1 squared. It's going to be equal to negative 2 mv1 squared.
Right.
Crashes into that one.
Sense.
Is that the same thing? So it's 1 squared.
Can't do that.
Not the same.
Not rational to say it's not the same. Just like right up there, has to be the same. You have to conserve the force in terms of the same force has to be the same work.
So it does matter. You can't just double the speed of one and hold the other one stationary and crash them and expect to get the same kind of damage.
Yes, you can. The damage will be exactly the same. So again, it's just a lie to say if you put something that's not on the wall and it's not on the other object, so the crushable thing will be in between the collision. When you hit it 50-50, it's going to be exactly the same crushing as if you hit it 100 miles an hour into the wall on the other side. So if you use the same crushable substance in the two experiments, the crushable substance, the force meter, the impact collector, will collect exactly the same amount of work.
But wait, there is a way to make it work. Because let's say I did the following. Let's say I have my case 1.
So you want to be a software engineer. Go to boot.dev, make a free account, write some code.
And those are in meters per second. Physics shouldn't matter where we put our coordinate system. It shouldn't matter if I put this as the origin or if I put the origin over here. It should, because the origin's not real, it shouldn't matter. It also shouldn't matter.
All this relativity crap doesn't make any, yes, it's all just such woo. Ugh, disgusting. Waste of time. People get involved in this mush, try to rationalize some sort of frame. Like somehow you can actually move physically into some frame where the physics is different. They're claiming it's the same, and then they claim it's different. That somehow I can have a frame that is doing something outside of what that universe outside of the frame is doing. And I can't do anything outside of that universe.
The velocity of the center of mass of my coordinate system. So what if I have this coordinate system, but my coordinate system is moving this way at 50 meters per second? And this is what we call relativity.
It doesn't mean anything. You're not going to change what happens between those two objects because you're changing your perspective. Your perspective will not change what happens to the two objects.
Because the motion of these things should be independent of the velocity of the frame, up to a point. Okay, if you start getting near the speed of light, things don't work. But this is low speed relativity. So in that case, if I have this, here's my new coordinate system. It's moving to the right at 50 meters per second. Then this car, according to that coordinate system, is just sitting there.
Right. The other car
And
is going
this
100.
car is moving this way at 100 meters per second.
Right. So you just proved the argument right there that you can't change the impact by changing your perspective. So obviously you're conceding the point that the collision actually has to be exactly the same. So I can't make a claim that there's a difference between these two experiments because just by moving my perspective, I can create both those experiments. So they can't have different outcomes. They have to have the same outcome. So you're just proving the point that they can't possibly have different kinetic energies because the outcome will be exactly the same.
So let's do this problem where
The effect on the two cars can't be changed by you moving your perspective. By you moving with one of them or moving with the other one, you can't change what happens to them. Oh, God, duh.
which is, in this coordinate system, I have this one moving at 100 and that one's not moving at all before the collision. And then after the collision, we let it do whatever it wants. Okay? Because that's the same thing. That's the same thing as this. So let's start with momentum in this coordinate system. So I'm going to say P total 1 equals P total 2.
You can't change the momentum, so it's a waste of time.
So I have, before the collision, I have M 2V1 plus M times 0 equals, now they stick together. Okay, I'm going to say they stick together. So this is going to be 2M.
All right, so sticking together means they're crushing something, frankly. Okay, just sticking together, there's no way you could really imagine two cars that you could smash into each other at 50 miles an hour and they stick together. Not going to happen. Not if they're made out of normal materials on Earth.
Times V2. Now you see here that V2 is not 0. So the masses cancel and I get V2 equals V1. So after the collision, it looks like this in my coordinate system. I have the two cars stuck together, but they're moving with a velocity v1. And that makes sense because if this reference frame is moving to the right at
They stopped and you didn't. That's all you're saying. So they hit each other, they stopped moving, you're still moving. So yeah, they look like they're going that way, but you can know that's just an illusion because you're moving.
the speed of v1, then those are like stationary in the other frame. So all these situations agree with each other, and that's important. Okay, but this is important too, because now I need to look at...
They all agree with each other as long as you're conserving momentum, but as soon as you try to conserve kinetic energy, they won't agree with each other, and that's the proof that the kinetic energy is bullshit, because as soon as you apply these principles using kinetic energy, you're going to be running into the problem that now you have that v squared problem. So now you're going to be squaring something with twice the velocity. Squaring something with twice the velocity is going to get you 4 times the energy as 4 times. So it's going to be twice the energy. And you can't have made twice the energy by changing your perspective. Your perspective can't make twice the energy happen. So it didn't happen, clearly, which means it doesn't happen. It's bullshit.
the change in kinetic energy. So let's put delta K is going to be the final kinetic energy. So in the final case, I have 1/2, and I have the mass of 2m, and then the velocity is v1, right, because I have that. So v1 squared. That's my final. Minus the initial kinetic energy, I have this one, which is 1/2 times m times 2v1 squared. And then that one doesn't have any kinetic energy, minus 1/2 m times 0 squared. So this is going to be m v1 squared.
So that doesn't even make any sense. He said they both stick together, so they both have to be moving after. So I don't know what the 0 one is, but whatever.
This is
I guess that's his claim of initial.
going to be minus, I have 4 m 1/2 4 mv squared, so it's going to be minus 2 m v1 squared. So it's going to be minus,
So he just put the,
and then
why did he just
double
do
the
that? I mean,
speed.
it's so stupid. He
In
put
this
the
coordinate
two-
system, I have this one moving at 100, and that one's not moving at all. M times 0 squared. So this is going to be,
It didn't make any sense. He just says it's 2m. It's not going to be 2m. It's 2v, you said. So in the v is a real v number. So you've got twice the v number you're squaring.
m v1 squared. This is going to be minus, I have 4 m 1/2 4 mv squared, so it's going to be,
There's no 4m. There's no 4m. So he's got that just way off. It's obviously 4 v's. I mean, it's 2 times v, and then that number squared.
minus 2 m
See,
v1
cheat right there. All wrong. No, you did it wrong.
squared. So it's going to be minus m v1 squared, because I have m v1 squared minus 2 m v1 squared is that. And that's my delta K. That tells me damage, right? Because that's the opposite of the change in internal energy. And if you go back over here,
So again, he's just making up this fake notion that you do damage when there's kinetic energy. You don't do damage when there's momentum. It just doesn't make any sense. And obviously that was just absolute garbage math. The 100-mile-an-hour illusion, and that's all it is an illusion, that one of the cars is going 100 and the other car is not moving. So when you're moving with one of the cars, and the other car looks like it's moving 100, it's really not, but kinetic energy says it is. Your perception matters, and obviously it can't matter. So it shows that either relativity is nonsense, or it shows that the kinetic energy theory is nonsense. You can't have it both ways, because the fact is, it doesn't happen. There won't be a different outcome to the experiment because you are moving with one of the objects. Obviously, your perception can't change what happens. All right. Slightly difficult to watch with the people's head image. We get it. You don't like the guy. I don't even know what that means. PP head image. Oh, that bothers you? Oh, I wonder if you must have a little bit of blue moonshine up your ass. Yeah, should I make it bigger just for you? Yeah, maybe just for you. Okay. Look, the man is a psychotic, and he's a fucking physics teacher at a university, and he's a psychotic lunatic. It sort of needs to be emphasized. Yeah, really. That's how bad it is. That's how bad education in America is that this psychotic lunatic at this, which is probably just a diploma mill university. I don't think anybody graduates who has any knowledge at all. I bet there's not a single physics student at Xavier University that knows anything about physics at all. He's only there to pretend to be a scientist. But yeah, fuck you. You're ridiculous. I'm sure you have equations in books that could help. So again, fuck you in the ass till dead. Where's your equation defending 1/2 mv squared? Show me your experiment. Right there, the experiment saying it doesn't exist. This little experiment right there saying, fuck you. Do you really think that one cart that got the same exact force has 8 times the energy? You think so? Well, it's going 4 times the velocity, right? So it's going 4 times the velocity. So yeah, it comes down the end to it having 4 times the energy, right? 4 times the velocity is 16 times, let's see. Yeah, I got to do the math here. All right, so the one thing is going 1v, the other one's going 4v. And then you square that number, so that is 16, and this is 1. Yeah, so it's 16 to 1. You really think the car going 4 times as fast has 16 times the energy? Even though it's exactly the same fan blowing the same energy, that somehow that thing has collected 16 times the capacity to do work. You think that's fucking true. And you're gonna question my equations or my math or my logic, and you're gonna claim something that fucking ridiculous that you can never ever prove, and every fucking experiment demonstrates to be absolute shit? No, you're the asshole, fuckhead. Let's see. Yes, just the diploma mill, yes. And that'll be demonstrated too. Look, I've already outed him, okay? He did a fake experiment, all right, and he's stuck with it. He'll never do the 4 rubber band test, okay, with his air track. He'll never do the legitimate experiment because he couldn't even do the simple one without cheating. And that was demonstrated. All right, well, then what are you doing here? True, I'm an asshole. I agree. Then we'll go somewhere else then. What do you think? I want assholes fucking around? I don't need to waste my time playing with somebody's asshole. I'm not an asshole kind of guy. I just don't go there. It's not my thing. I mean, I know there's a lot of people like doing things with assholes, but I don't really like them. I find them smelly and creepy. So take it someplace else. Take your asshole someplace else. All right, let me finish this fucking video.
Here, this is the same thing we got before when the 2 cars were moving at the same speed. Okay.
So yeah, but you didn't do the math right, moron. So yeah, you got the wrong answer. Oh,
so
amazing.
Everything works, and in fact,
silly person. Obviously, it didn't work at all. You can't change the amount of work being done in the experiment, okay, the amount of kinetic energy it has based on your motion and how you look at it. You can't change what it does by looking at it differently. You can't do that. Ha ha ha, you fail.
In fact, if you want to do this in the normal reference frame, you would, right? I could have a car moving at 100 meters per second and one at 0, and I would get the same damage if I let them recoil. Because it doesn't matter which frame I'm in.
All right, so you can't have damage if you let them recoil. You just said that, right? I can show you I have the same damage if I let them recoil. Shit.
And it doesn't matter about those things. Okay.
They can't be elastic and inelastic, and if they're somewhere in between, then there's no rules, frankly. There's no guiding principle that tells you exactly what you're going to end up with, because the proportions of energy will be mixed. I mean, how much heat you create, how much deformation you end up with will depend on variables that you probably can't account for.
But once I kind of lock this down with a wall, then I'm adding extra force into the system.
No, there's no extra force. Silly shit.
This.
Silly, silly, silly. Reflections are not extra force. The anvil does not keep the ball bearing bouncing. The anvil's not pushing the ball bearing up 270 times. Right? So if I bounce it on a hardened anvil, right, the ball bearing will bounce 270 times. The anvil is not bouncing the ball bearing up in the air. The anvil is not accepting the energy, and it's giving it back to the ball bearing in exactly the opposite direction.
Is not the same.
It's a reflection. It's a real thing, reflections. All right, let's see. Hates himself. That's sad. Well, whatever. Yes, hating yourself is pointless. No. We're all frail. Okay. And fallible. You can argue that, there's some part of you that's just trying to do the right thing. And you're just blinded by religion or bigotry or some other kind of crap. But I can't read your mind, I can't sense your soul, and figure out what your agenda is. But I'm just saying, if you're going to sit there and just blindly defend conventional physics, you're a dupe and a fool, and you're going to waste your life defending garbage and such. Just a fact. Let's see what else we can find. I guess let's finish this first. So it is disappointing. It's got the same damn channel. So the one channel is called Dot Physics. So let's see how many videos this channel has. Okay. One day ago. Okay, so this is more recent stuff too. So maybe he just made this channel or something. Well, 55,000 subscribers is a lot. But he gets no views. So how can you have 55,000 subscribers and get 98 views on your videos? That's pretty terrible. Alright, so let's see. Tension in a Batman wire. Alright, we're not doing that. Find the spring constant for a block on... Well, we're not doing the ramp thing. That's just a cheat. Let's see if he does anything good in here. Ball hits a stick in the center or edge, which is faster. Ball hits a stick in the center or edge. Well, obviously it's not gonna, if it hits the edge, it's gonna have to create a whole bunch more momentum. So, yeah. Let's see. Python physics. What is he calling that? Modeling collision with an auto blaster. Astro blaster. What's an astro blaster? I don't think we'll bother with that. Let's see. Modeling rigid objects with springs. I don't know. That doesn't sound like a good idea either. Chapter 5 summary. No. 4. Let's see if we can get to anything energy-wise again. There's so many good, magnetic videos that I have to get to. So many people talking such shit. Let's see. Rotating due to a solenoid. Yeah, well, that's probably crap too. Electron spin, that's probably one to do. Is an electron a spinning charged sphere? Well, we know it's not. But yeah, let's try a simpler subject. How about 2 months ago? Yeah, okay. It's got a lot of videos here, so some of these might have been made way before 2 months ago. Now, let me see how many we got. Maybe see if we can get out of the electrical stuff. See if we can get to. There's the word physics. So, right, two white one wrong way to make a spherical. No, we won't bother with that. Gradient vector. Work energy. Here we go. All right. Yeah, we don't want dilation. Weight, gravity, and specific models. Scientific models. Let's see. Gravity is always a good subject because he'll definitely have that all wrong. Is this stick pull up even possible? What does that even mean? Be nice if he had a lever video, right? Yeah, that would be great. Well, I'll have to go through all this someday. Yeah, so let's just pick one for now. All right, we'll go back to this work and energy thing. It might be worth listening to.
Let's go, boys!
One thing I've noticed about football fans is they all talk like the players can actually hear them.
Proud of you.
The work energy principle.
Right, we're actually watching a fucking cartoon fucking lizard sell people crap. You know, so yeah. Oh yeah. Let's see. Question about the drop test. You want the test to go for 1 second. What does that even mean? Question about the drop test. I don't know. If so, that would disregard 9.8 meters per second squared. I agree, but it doesn't disprove reaching terminal velocity. What the fuck are you talking about? Nothing's going to reach terminal velocity in a in a test where you're not going to go any faster than 9.8 meters per second. Or 19.6 meters per second. I mean, if you did a drop test where the height is 4.9, so 5 meters and 20 meters. Yeah. So it's 5 meters and 20 meters. That's the drop test. Then it would be at 2 seconds for the 20 meters, and it'd be 1 second for the 5 meters. But I don't even know why you're bringing that up exactly. I mean, it's not today's video, but whatever. Whatever.
I'm not really happy with the way most textbooks treat the work energy principle, so I'm going to make my as short as humanly possible summary video about the work energy principle. Just a quick note.
Yeah, it is. You know, and so unfortunately, I really can't talk about any of these subjects without taking 43 minutes. And you know, people want done 5 or 2, and it just, you know, it's just really hard to be fair to these subjects in that amount of time.
You know, my ideas are influenced by other books. My favorite book, Shabai and Sherwood, Matter and Interactions. So it's basically that stuff.
All right, so what are you asking me now? So, let's see. Let's see. So if I would disregard 9.8 meters per second squared, so there's no second squared, so that's something you shouldn't be doing anyway. All right, so he's just, yeah, it's the comment I already read.
But let's just get to it. We have some stuff to cover. We have some prereqs. I made a little list so I wouldn't forget. So we're going to talk about forces and how you represent those as vectors.
And then we could talk about why do you have two channels, and what's the whole point of doing that, and this looks kind of whatever, sneaky or something.
And just so that we can go through the different options, the dot product, a way to operate two vectors together. Then we'll talk about the work energy principle.
All right, so we know all of that mathematics. Okay, it'll be a waste of time. Because it's really all there is MV, and there is nothing else. And force is work, and force is weight, and force is momentum. So it's all the same thing. So you don't need any dot products.
And why you would use that. We will talk about a very simple system and choosing systems, and then we'll do a complex systems, and then I'll talk about the types of energy, and then that'll be it. Now,
yeah, there's no types of energy. So all energy is really in the form of this stuff called force, and you either give something force, and it possesses it, and it can exchange it. It can give it to something else, and that's all there is. And yes, relatively speaking, we can't tell who's moving. If this is moving this way and this is we can't tell if who's doing what, theoretically. Now, I'd argue we can tell if we actually do let them hit each other, because it does matter who's moving. But anyway, leave us continue.
And there's a whole bunch of stuff that you could do with this, and there's more complicated things too, but we're gonna stick to the basics, right? Basic stuff. Okay, so let's talk about forces. Remember that if I have some force, let's just even say it's some force F like that. How do I represent that force as a vector? Well,
yeah, you just did. So again, it shouldn't be even a little bit complicated. It's motion, and so you can see it. And so in the things right up here, it's just motion. They have vectors in that direction. They have an arrow. They're not moving in all directions. There's not arrows going in all directions. That's like heat dissipation. When heat dissipates, well, then you have lots of vectors. But when you have linear motion, you don't have lots of vectors.
The easiest thing is to say, well, it has some x component this way, I call that fx, and it has some y component that way, fy. And so now, how do I represent that, write that down? You could even have it in a z direction too, right? That's the x direction, y direction, that's the z direction.
Right, but you have to get the, common reference frame correct before you worry about other reference frames. So first you have to be able to agree on the simple two-dimensional exchanges and what's possible. And once you have that, then you can worry about doing the three-dimensional vector math. But you first have to get this right, that this is just a vector of a magnitude, and that's all there is. There's no scalar vector. There's no scalar magnitudes.
But there's a couple ways that we could represent this vector. One is to write it like this. F is fx in the x direction plus fy in the y direction. Okay, so that says how much in the x, how much in the y. And you think, well, hey, I thought we're doing work energy. Why do we care about that? It's going to matter. Another common way is to write this as f as the x component, and then they use I hat plus the y component, and they do j hat. And then these both have a k, a z component, a z hat. You could do that. Plus fz k hat. So those are really the same representation.
All right, so this is sort of going to be a waste of time because, all of this analysis, this only matters once you first establish that there's only force that's in magnitudes of weight. And that's all there is. It's just weight. It's just pressure that you can apply to a surface, to another object. You're just going to exchange it.
In the first semester of physics, we like to do things in 2D because we can.
Yes, leave it there.
But it's important to realize that we live in a 3D world, and in the second semester of physics, when you get to magnetic fields, you can't do it in 2D. It's a 3D thing, so I'm just letting you know. And then finally, the way I like to write it, this comes also from matter and interactions, is like this. So we can just write the x, y, and z as a triplet, fx, fy, fz. Okay, but these are all numbers, right?
So they're numerical values. They could have numerical values for them. So I could have something like F equals, I'll write it in that format, 2x hat minus 3y hat. And then I could write that in my format as 2, -3, 0. I'm going to always include that z direction just because it's easy. It doesn't really take up much room. See, here I have 3 components, and it takes up as much space as that. It's all about the space, people. It's space. Okay. So that's how we, one of the ways that we represent vectors. Here we're going to use 2 types of vectors, the force vector and the displacement vector, but they're both in that same format.
So the displacement vector is the one that's just wrong. So force isn't anything about distance or displacements. It's about how long the propellers are spinning on those fans. And that's all that matters. How long are the propellers spinning on the fans? That'll tell you how much energy those objects will absorb. Not any displacement crap.
Okay, forces, dot product. Now, we've already looked at forces before. We found the magnitude of a force. We found, we added forces, we subtracted forces.
I missed all that, damn.
We multiplied the force by a scalar, right? If you did.
Okay, so yeah, the scalar. The magical woo energy.
MA, that's a vector, but I multiply it by a scalar. That's cool. Okay, you can do that.
So whatever that means, so it's a scalar, but it's a vector.
But now we're going to do a new thing with the vector, and it's called the dot product.
And Doug.
Imagine if we could tell everyone here that Liberty Mutual customized.
All right, I don't think we're going to mess with dot products, waste of time. So let's see if it gets to anything interesting.
How would we use the work energy principle? Let me say what it is. So let me first define work. Work
has nothing to do with doing anything like work. So, it's not like, okay, you have a rocket and you're going to shoot a bunch of exhaust out of your rocket, a bunch of matter moving at velocity. And it's going to have a momentum and it's going to have a kinetic energy number. And the kinetic energy number is going to be gigantic because it's little stuff you're throwing at very high speeds. So, it'll be a gigantic number. But your spaceship is only going to move with the momentum number. So the kinetic energy number won't mean anything. It won't do any work. So you can't get kinetic energy to do any work in space. So it can't make something go anywhere. It can't make something move somewhere or get somewhere. It's absolutely useless. Okay, it has no practical use, the kinetic energy. Having a higher kinetic energy won't get you more motion. Fact. So you might as well just throw chairs out of your rocket to move it, because throwing little pieces faster won't get you anywhere. Fact. And it won't be collected in a ballistic pendulum, and it won't work on levers, and it won't work on pulleys, and it won't work anywhere. It doesn't do any work, and it doesn't work. It doesn't make any sense. This is not the same work as this. Not the same work.
We define as W is the vector F, some applied force dot a displacement delta R.
So, and it's really force times time. So the amount of time, how long are those propellers on? That's how much force they will collect. How long you're in the sun will decide how much suntan you get. How long you're in the wind will decide how fast your boat goes. Blah, 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 blah. And on and on and on.
And now you could write that.
How long you're in the gravity will decide how much force has been transferred through you or to you. Obviously, if something is dragging you, you're in gravity, but you're not allowed to free fall because something's frictioning you. You know, you're tied to a string, or you're rubbing on a surface and you can't fall. You're then your time in gravity will be converted into heat, and you'll make more and more of it. The slower you drag on the sandpaper, the more force you'll put into the sandpaper. And the slower you fall on a string, the more force, more tension you put into the string. These are all facts. It's about time, time, time. Gravity is collected in units of time. It's 9.8 meters per second over 1 second. It is not seconds squared. It's over 1 second. Oh, how many times have I had to say that? No comments. Okay.
Is F delta R cosine theta. See, there's those two definitions of the dot product, right? I have the vector version and the non-vector version. Either one's fine. But if I push on an object over some distance, then I'm going to do work on that. And that work...
So we know right there, we have the example. This is his experiment right here. This is his experiment. And he's seeing it doing the work. We have the same force. So it's doing the same work on these two objects. And one of them is just showing you that you have 4 times the, the mass and 1 unit of velocity, and the other one has 4 units of velocity and 1 unit of mass, and you've perfectly conserved the momentum of the force. And there's absolutely no reason to think you made 16 times the energy. That you're going to do 16 times the work with one of these carts that you're going to do with the other one. The yellow cart is not going to do 16 times the work. It's not going to happen. It's not going to knock down 16 times more doors. It's not going to knock down 16 times more bowling pins. It's not going to do a damn thing to demonstrate it has 16 times the capacity to do work, because it doesn't. Well, it's not 16 times because it is only 1 unit of velocity. So again, it's 4 times the work. It's not going to do 4 times the work. It can't do 4 times the work.
Is the change in energy of the system. And we'll talk about the system in a second. Okay. But more importantly, why would I do that? We would do the work energy principle because work is a scalar, that's a scalar value, and the change in energy is a scalar value.
So again, you say so, but it doesn't show so. So there's just no evidence of it. So you brought up Mythbusters. Mythbusters essentially is a pretty clear proof that kinetic energy didn't show itself in the experiment. Your own experiments right here aren't showing kinetic energy doing anything called working. It's not showing the same force, okay, producing anything but the same momentum. And that's all it can do, because that's all it is. The force is momentum. That's Newton's statement. 1 unit of force, 1 unit of velocity. 2 units of force, 2 units of velocity. 3 units of force, 3 units of velocity.
That's the first thing. It's not a vector equation. The second thing is that this deals with a change in position, not a change in time. So when we're dealing with things, we don't really care how long it takes. We only care about it starts here. Then we can use the work energy principle. So that's why we're going to use it. So it's a different way of thinking about things.
And it's wrong. So MGH is wrong, and W equals F times D is wrong.
Is it possible to solve a problem both with Newton's second law and work energy? 100%.
So again,
is one easier than the
It's ridiculous. So again, you get different answers. You use Newton's physics, you get a different answer. It's not the same answer. If you use one mathematical theory to land on the moon, you'll land on the moon, and the other one will crash you. Only one of them can work, because they'll give you 2 different answers about how long to leave that thruster on. So the fact that they'll give you 2 different answers means there can't both be compatible theories. One of them's right, and one of them's crap. And it's just unfortunate that you people have all chosen to hug the crap water, and instead of the sensible physical understanding. Just unfortunate. You've been stupid.
Yeah, there's sometimes, yes. Or sometimes it doesn't really matter which one, yes. If it was a test question and it didn't say to use the work energy principle and you solved it with Newton's second law, would I take off? I wouldn't. I didn't tell you, right? You solved the problem, you solved the problem. Someone else.
Right, so it doesn't matter which theory you believe in. You just solve it with one answer or the other answer. It doesn't matter that the answers don't agree. Oh, great. Fantastic. That doesn't seem like reasonable physics.
Might, but they shouldn't. Okay. Let's go ahead and talk about choosing a system, because this says the work done on a system. So imagine that I have some group of stuff and I'm pushing on it. That is going to do work, and that work is going to change the energy of the system. But what is my system? It tells me what.
So again, work is energy, right? So he's making this argument, but he thinks it's kinetic energy. And no, it's momentum. So work, pressure, weight, energy, heat. These are all the same exact thing. There's no difference, because it's all made of the same elemental function, which is the collection of force. And it's those little force bits moving the speed of light that you're collecting. You're collecting quanta. Okay, energy quanta. That's what's in the universe. It's Sisyphuses and boulders.
What does work, and what kind of changes in energy that we have. So let's just take the simplest case, the simplest situation, and do a problem. I'm trying to think, should I erase this? I'm going to erase this so I have more room. I like this side of the board better. So let's
Whatever.
erase this side of the board, and then I'm going to use the work energy principle to find out the speed of a ball that falls. Simple problem, right? But it'll help us.
Right. Yeah, but I mean, the point is that it's obviously what time you're in the gravity. Granted, gravity says it's obviously demonstratable to be. I mean, I just don't know how anybody can deny what Newton's called it. I mean, it's in 1 second units. That's what Galileo figured out. That's what Newton did, is in terms of you have to put it in some kind of timed units. And the timed units works. It's a consistent amount of force you collect in a consistent amount of time. And, and how big your mass is will decide how much force you collect, but you're always going to collect the same velocity, because your force will be proportional to the mass you have, and each electron will collect exactly the same amount of momentum. That's all that's collecting it, is your atomic bits. Your atomic weight is essentially collecting your momentum, the momentum you will collect. And each atomic bit is exactly the same, collecting exactly the same amount. So if you have more electrons and protons, you'll collect more energy from the force. And you'll hit the ground and release more energy because you collected more. Duh.
Just kind of think about all this stuff. And we can do it a bunch of different ways. So here's my problem. I have the ground. I have a ball. It has a mass m. And it starts up here, position 1. I'll call that y1. And it's going to fall down here to y2. And then this is a height h. And up here, the velocity v1.
Right, and I could just redraw this and point out that, well, in the first, if I was to break this into 2 units of time, this falling process, in the first 1/4 of the distance, it's going to be going half the velocity. So after it moves just 1/4, it's already going half the velocity. And in the next 3/4 of the distance, it's only going to gain 1 more unit of velocity. And that lack of symmetry is just kind of glaring in terms of how this object will fall. And it's always going to do this 1 to 3 thing. You don't even have to go 5, 7, 9. You can just understand the ratio is always 1 to 3. Any distance can be broken up into 1 to 3. 1 to 3. You're always going half your speed after you've only fallen 1/4 of your voyage.
Is 0 meters per second, and down here v2 is I don't know. And I want to find that final velocity.
As an executive, I see no value in you. Your noxious odors.
So with the work energy principle, I think the most important thing, and a lot of textbooks drop this out, is the idea of choosing a system. So I want to pick a system. I'm going to go ahead and say it, system. What is, if I want to use the work energy principle, what am I doing it on?
Well, you're just saying that it doesn't matter because any force, okay, it's going to just depend on how long you're in, how long you're in the paint spray, how long are the sandblasters hitting you. I mean, no matter what it is that I'm using to push you, whether it's a stream of water or a stream of wind or a stream of gravity or a stream of light or a stream of anything, it's really just going to depend on how long were you in the force. How long was the force impacting you? And obviously, if it's a constant force or a consistent force, those rules will be the same for all of those, and they'll all do 1, 3, 5, 7, 9. They'll all do that ratio. They'll all behave just like gravity because they're all the same kind of force. And the big difference is gravity, like photons, is moving the speed of light. See, when the little fans are blowing on those objects and pushing the things up here, there's a point where they can't go any faster, so they won't be accelerating anymore because they'll have reached the capacity of the fan. They're going as fast as the fan can push air, and that's it. They can't go any faster. So, but you're not going to outrun a photon. You know, it's going to take a long time for photons to get you to be moving the speed of photons, and it's going to take a long time. You have to fall in a large gravitational field to ever reach the speed of the gravity. If so, that would, okay, guys, you're at the same comment. So there's no new comment, so maybe I'll just call it a video soon, because looks like there isn't much participation here. 7 viewers, yeah, mediocre. I did email the guy about the simulation, but he's not here, so but I didn't get any reply, so I don't know if he got my email. It's just annoying that you know, there's all these email companies and all these, and they block your emails and you don't ask them to. It's like there's no button to hit where it says don't filter my emails, you stupid cunts, because you keep putting real emails in the trash and you keep feeding me the garbage ones anyway, so your filters suck, so please don't apply them. You know, I wish I could find that button. So I read the channel description of the new Feynman videos. Wow, yeah, it is, at least they do admit what they're doing, but whoa, I don't know why it's legal. I don't know why YouTube lets people do that. I mean, frankly, it's so obviously deceptive. I mean, they should require them to put a big, you know, AI fake on it or something. You know, some real acknowledgement that this video is not the person they're pretending it is. And there's, like I said, there's so many. I don't know that why. Maybe it's only like 2 people that are doing all this. You know, they're creating all these channels, but it's like there's literally like 6 or 7 new channels created just to do these fake Feynman videos. It's just, yeah. I don't know. Nobody's calling bullshit. There's a lot of shit needs to be, somebody's got to call bullshit, and nobody calls bullshit. All right, so I'll play a little bit more of this, but I don't think it's going to go anywhere.
It depends, right? Okay, so in this case, I'm just going to pick the ball. That's my only system. So that means there's 2 things that are important. Any external interactions will do work. So the work is from external interactions. And then the change in energy depends on my system. In this case, the change in energy is going to be kinetic energy.
Right. He's claiming you're going to collect it in units of distance. And so that's the idiotic part. Clearly, it's not how gravity works. It's not how Newton understood gravity to work. He was quite specific in arguing about how it's in units of time. And that's even his calculus was based on units of time. Leibniz's was units of distance. So again, that's the difference between the two calculuses. So this whole thing is just such bullshit.
So kinetic energy is 1/2 mv squared. So if I only have a point mass, it can only have kinetic energy. I mean, you could say it has, let's just say that. I'm not even going to say the more complicated version just to be right. I'm not going to do that. Okay.
Whatever that even means. The more complicated version to be right. I'm not going to bother with the complicated version that's right. I'm just going to talk shit. Oh, okay.
Okay. So it can only have kinetic energy if it's a point mass. That's all.
So again, it says you, and it doesn't make any sense, and it's stupid, and it's wrong. Again, by their theory, okay, I dropped two objects, a 1 mass 4 units of distance, a 4 mass 1 unit of distance. The fact is, the 4 mass is going to be going half as fast as the 1 mass. Half as fast, not 1/4 as fast. So they're not going to have the same momentum, and yet they're going to tell us that they do the same work. So even though one of them has twice the momentum, they're going to do the same work. And they think people should believe that without any visible evidence of it being true. Without him being able to show me any experiment demonstrating that to be true, I'm supposed to believe it. I think that's really bad science. That's very good religion, but it's really bad science.
Kind of energy it can have. So we know what we need to find out what forces are doing external work on it, and we set that equal to the change in energy. Okay, let's start off with the work. So work is F dot delta R. Well, it's going from here to there, so I need to find delta R.
So I don't know why delta R instead of delta D, but whatever. Too ridiculous again. It's hardly a radius.
Well, let's just write that out, okay? So I'm going to say up here, I'm going to say this is delta R. I need to find that. Delta R is going to be R2 minus R1. I'm going to do this as a vector, okay?
R2 minus R1. What is R2? Where's R2? where could R2 possibly be? Oh, you mean on the surface, and then you're going to lift it up and call that R2? I don't know.
So I'm going to pick down here y equals 0. This is my y equals 0 value.
Thank you.
And then that's actually my origin. So that's y is equal to 0, x equals 0, z equals 0, 0, 0, 0. Okay. So down here, I can say R2 is equal to the vector 0, 0, 0. What about up here? What's my position up here? Well, R1 is going to be 0, h, 0, right? Because it's a height h. So if I go up h, that's where it would be. Well, now I can find delta r. Delta r is going to be R2 minus R1.
Yeah,
and I can subtract vectors.
You already did that, right? You got that written down right over here. So yeah, we're already done with that r crap. We already figured this out. Right, it's 1 minus 0. Yeah, we got it.
Right? R
1h minus 0. Yeah.
R2 minus R1 is going to be 0 minus 0.
This is day 1 of my husband doing Tai Chi workouts. This is day 21 of my husband doing Tai Chi workouts.
Yeah, sure.
0 minus.
She married a 70-year-old man. Hilarious. That happens all the time. Yeah, all the time.
This h is negative h. 0 minus 0 is 0. So now I have my delta r. And you don't actually have to do it.
Which is h, you're right. So you have nothing. I mean, you just, what a waste of time. I mean, this is where math just waste, what a waste of time. Why would anybody waste all their time with all this horse shit and just say, look, okay, it's going to be a height of 1 meter. Why waste all this time?
that way, right? I don't really care about R. I don't care about R1. I don't care about R2. I care about the displacement. If you just said...
Right, so again, it's just this displacement number, which means absolutely nothing in this context because gravity is time dependent. You collect it in units of time. You collect gravity in units of time. All right. All right, so yeah, it's I guess there's just nobody else here that wishes to converse. So yeah, I think I'm tired enough, and I will say good night. And I'll look over these videos and see. Maybe I'll send the guy an email and see if we get him to interact in a constructive way and such. Oh, somebody's talking a foreign language at him. I would have said potential energy is mgh, and it is converted into kinetic energy since the total energy of the system doesn't change. Maybe I am wrong. Don't know. Yeah, why would you bother with these silly words when all it's going to create is momentum? All you're going to create is an mv. Why do you think there's an mv squared? Why do you believe it? Where have you seen evidence of the squared thing producing any effective motion in the universe? Again, it doesn't even work with a rocket fuel. Alright, when you start drawing the pendulum, I thought you were going to do the double pendulum. Ha ha ha, really nice summary of this material. No, it's a really horrible summary, frankly. But whatever. It's all that's in town for the moment, and so this is what we'll deal with. But anyway, okay, so I guess that's enough. Yes, you're very fast to say goodnight, aren't you? Yeah, you're all wanting to go. Oh, please let us go. Oh, I can't stand looking at you, raghead. Oh, why don't you just shut the fuck up? You're so fucking redundant. Anyway. Yeah, too bad. Haha, I made you stay. All right, now I'll let you go. You're free to go. Okay, I'll give you permission to leave. Blah, 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 blah. Goddamn weasel. If I can embarrass some fucking goddamn YouTube audience, pile of fucking moron, fucking assholes, and all this shit I have to go through. Hate this damn planet. Alright, anyway, till the next time, and such. Thank you for the participants that participated. I like that. Participated.